Swayamprabha. Digital India. Educated India.
Welcome you all. We are now on to module 3 of this MOOC course. Last 2 classes we have done some review on mathematical formulation, operators, important properties, description of the flow, and then we started doing equations. So, we first did conservation of mass or continuity equation, then we went on to momentum equation, which is called conservation of momentum, and we have written a momentum equation in both vector form as well as in scalar form, and that is repeated here, all the 3 components of the momentum equation, and we know this is also called Navier-Stokes equation. We recognize here again the first term is unsteady term or local acceleration, the remaining 3 terms are convective acceleration. Like we did in conservation of mass, if you simplify for different situation, then the original generic continuity equation gets reduced as 2 dimensional only with the spatial derivative. Similarly, conservation of momentum equation also can be reduced for different simplified situation. For example, if you say the flow is frictionless, then effect of viscosity mu term is negligible. So, in the Navier-Stokes equation, mu term appearing as a viscous stress term on the right hand side. So, that term is removed and you get resultant equation as Euler equation. So, left hand side remains the same, d by dt total derivative of the velocity. There is one term that is removed because of the viscous effect is not considered. The external force term and pressure term remains the same. So, this equation is derived or deduced by scientist Euler, hence the name is given as Euler equation. So, theoretically for any inviscid where viscous effect is not there, an incompressible flow, you can directly either Navier-Stokes equation and momentum equation can be used to obtain pressure as well as velocity field. Okay. So, you can also integrate this Euler equation along a streamline, and after some simplification it results in what is known as Bernoulli's equation, and that is given here, P by rho plus V squared by 2 plus G Z equal to constant. We know Bernoulli's equation is an energy equation. So, you get a pressure energy, kinetic energy or velocity energy and potential energy. So, Euler equation, if you integrate along a streamline, then you get a Bernoulli's equation. So, Euler equation is derived or deduced for frictionless flow. So, Bernoulli's equation is with the restriction for only frictionless flow. You can also obtain Bernoulli's equation for unsteady flow also. So, next third equation, which is conservation of energy equation. Once again we are not going to the details of the derivation steps. We first state the energy equation itself, which is given here as rate of change in kinetic and internal energy is equal to sum of net inflow of the kinetic energy, work done by the body forces and net work done by the stress field as well as net heat flow. And this definition is applied, then there are many arithmetic operation. Finally, the form that is given here is given dou rho Cv d by dt of temperature on left hand side, and there are 3 other terms on the right hand side. So, in this equation Cv is a coefficient of specific heat and constant volume, and K is a coefficient of thermal conductivity, and Q is any external heat source, and phi is the rate of dissipation of mechanical energy, and that is given by this expression. So, in this expression is the summation, and this tau ij rho ui by dou xj, where I and j are indices representing direction 1, 2, 3. So, if you substitute I is equal to 1, j is equal to 1, 2, 3, I is equal to j is equal to 1, 2, 3, I is equal to 3, j is equal to 1 to 3, you get so many components in this equation. This index notation is also otherwise called tensor notation. We are not going to the details of the tensor notation here, only this term is expressed in this form. So, as I mentioned before, from the definition, after for simple condition the equation is derived and it is given here, and there are other forms of the energy equation available in other references. As we did exercise how to simplify consideration of mass, consideration of momentum for different situation, consideration of energy equation is also simplified. So, in the case of incompressible flow, phi, which represent the energy dissipation, will be very, very small, hence the effect can be neglected from that equation. Similarly, if there is absence of external source, then energy equation gets reduced to only one term on the right hand side. So, in most equation, so we have consideration of mass and consideration of momentum. Consideration of momentum, of course, there are 3 explicit equations for each direction. So, in essence there are 4 equations, one for consideration of mass and 3 equations for consideration of momentum, x component, y component and z component. So, if you look at number of variables, you have u, v, w 3 and pressure 4. So, there are 4 unknown and there are 4 equations. So, mathematically it is a closed system of equations along with number of boundary conditions you specify, then you will be able to solve those 4 equations without any problem. If you are looking for only simple basic fluid mechanics problem, then those 4 equations are enough, and if you have a problem where energy transfer is also important, then you activate or include energy equations also. So, whether you solve energy equation in line with momentum equation or not is a question. If for most of the situation the energy equation is solved in a decoupled manner with the continuity and momentum equation. Well, what is the meaning of decouple? You solve mass equation and momentum equation, get a converged solution based on mass equation and momentum equation, then you trigger or activate the energy equation in the code, get a converged solution for energy equation, then move to the next iteration, the cycle repeats. So, this is what is known as a decoupled way of solving equations. But in problem where there is a natural convection, where temperature distribution causes a buoyancy force, then this procedure is not applicable. We need to solve energy equation coupled manner with a momentum equation, because in natural convection problem buoyancy force is an external acting as an external source term in the momentum equation. Hence, we have to solve energy equation as and when you are solving momentum equation, which is going again as a energy as a source term in the momentum equation. Next important topic is non-dimensionalization. What is the meaning of non-dimensionalization? It is a method or a procedure by which unit quantities are replaced. So, we have seen three major equations: mass, momentum and energy. In all the three equations we have also observed there are variables: velocity, density, gravity, viscosity, then temperature is there. So, in all these variables have units. So, is there a way by which you can remove the units and solve the equations in non-dimensional form? And there is a procedure, and that is known as a non-dimensionalization procedure. How do we do? We identify suitable variables and replace actual variable or non-dimensionalized actual variable by the corresponding suitable variable which is acceptable. Now, what is the advantage? So, it parameterizes the problem in place of units. So, this reduces number of parameters in the problem, and we can also identify by this procedure characteristic property of the system, which means there is a particular scale exists in a flow, either velocity scale or length scale or time scale. You can identify the corresponding scale by the non-dimensionalization, and that scale information is very helpful either to control the flow or manipulate the flow or to design a system based on that scale. Now, the advantage is, suppose you are running or doing experiment, running a simulation for one particular geometrical condition or flow condition, and there is a need to repeat for some other condition. If you do non-dimensionalization, then you do not have to do this repetition of cases for different situation. Results obtained one situation or condition can be obtained with the ease for another condition. So, in connection with that, we need to also know many non-dimensional numbers, and there are also many other important numbers. So, I am listing here only few of them. There may be more depending on the problem that you are studying. The first one is a Reynolds number. Usual symbol is given as Re, and which is a ratio of inertial force to the viscous force. Next is a capillary number, which is given a symbol Ca, which is a ratio of viscous force to surface tension. Froude number, which is used for, which is generally used flows where gravity effects are considered. So, it is defined as ratio of inertial force to the gravity force. Next non-dimensional number is a Weber number, again given a symbol W E, which is defined as ratio of inertial force to the surface tension force. So, it basically means whether inertia is dominating or surface tension force is dominating depending on the value of the number. In heat transfer context, you have Nusselt number, which is given a symbol Nu, and it is a ratio of convective heat transfer to conductive heat transfer. Then there is a Prandtl number Pr, which is ratio of momentum diffusivity to thermal diffusivity. There is one more number, what is known as a Stanton number, so which is defined based on heat transfer to thermal capacity, and it is also related to Nusselt number and Prandtl number as given here, Nu denominator Re multiplied by Pr. As I mentioned before, there are many more non-dimensional number for different problem. So, we have seen importance of non-dimensionalization and some important non-dimensional numbers. Now we are actually going to do non-dimensionalization of governing equation. We will do a detailed derivation for one equation, that is conservation of mass, and you can follow the procedure to get non-dimensional equation for other equations. So to do that, we need to define what is known as reference scales. So in a problem you need to identify reference length scale, reference velocity scale. If you consider, for example, flow through a circular cross section pipe, diameter of the pipe can be a reference length scale. If you consider flow through a rectangular cross section pipe, then hydraulic diameter, which is defined as 4A by P, where A is the area and P is the perimeter, that can be a length scale. If you consider flow over an aerofoil, the chord length can be a length scale. So one needs to identify which is a major influencing length scale in a problem. It may vary from problem to problem. Then one also needs to identify reference velocity scale. So again, if you consider flow through circular cross section pipe, if the inlet is uniform velocity, then uniform velocity can be a reference velocity scale. If the inlet is parabolic profile, either the bulk velocity can be a velocity scale, or the averaged, the middle maximum velocity can be a reference velocity scale. If you consider flow over a flat plate, the free stream velocity u infinity can be a reference velocity scale. So one needs to identify reference length scale and reference velocity scale. Once we do that, in the governing equation, all the length scale related quantities are non-dimensionalized with the reference scale. Similarly, all the velocity related quantities are non-dimensionalized by the reference velocity scale. And we also know you can get a time from velocity as well as length. So we will see how to do. Let us say, for example, all the length scale in all the length related information. So in this case x, y and z. So x is non-dimensionalized with L, and this non-dimensionalized quantity is referred with the symbol superscript star. So x star is non-dimensionalized length, and x is the length, actual length, and L is the reference length, and we know they both have the same unit. So x star has no unit. You can define similarly for other two dimensions, length dimension. We use the same length scale in all. So it is y over L and z over L, and t time is non-dimensionalized from these two. L over u infinity will give you the time. So any time related quantity, for example, first term, time derivative term, is divided by L over u infinity to get non-dimensionalized time t star. Similar manner you can also do for velocity. So it is u star is a non-dimensionalized velocity component in x direction, which is u is a velocity dimensional quantity, and u infinity is a reference velocity. So u over u infinity will give the non-dimensionalized velocity quantity u star. You can extend this to get v star and w star, and pressure is also another term appearing, and pressure is related to u infinity squared, and you define reference density. So if you take the unit of density and velocity squared, then you find the product of them has the same unit as pressure. So you are able to non-dimensionalize pressure term p over rho infinity u infinity squared will result in p star, which is non-dimensionalized pressure. And we have just now seen different non-dimensional number. So Reynolds number is appearing in momentum equation when you non-dimensionalized, and we know the definition of Reynolds number is the ratio of inertial force to the viscous force, and if you use this non-dimensionalized quantity, then finally you end up in expression for Reynolds number as rho infinity u infinity L by mu. Of course, you can define mu over rho infinity also as a nu, and Reynolds number becomes u infinity L over nu. So, all the star quantities are non-dimensionalized variable. Now that we have done the first exercise, we can repeat this, we can substitute this term in continuity equation to get a non-dimensionalized continuity equation. Now, we will try to do non-dimensionalization of the continuity equation. So, we know dou u by dou x and dou v by dou y and dou u by dou w by dou z equal to 0, and we just now learned how to represent them by length scale, velocity scale, and that is written here, and we also define u by u infinity as a u star and x over L as a x star and so on. So, we get rho u star by dou x star, dou v star by dou y star and dou w star by dou z star equal to 0. So, this equation is actually non-dimensionalized continuity equation. You can immediately observe none of the quantity have units. So, take any of this first term, for example, u star is already non-dimensionalized, there is no unit, x star is non-dimensionalized, there is no unit. Similarly, other two terms. So, no term has any unit. So, this entire equation has no unit. You can extend this procedure to get non-dimensionalized momentum equation, and that is given here. First term dou u star by dou t star, similarly u star dou u star by dou x star and so on up to last term also the viscous term. So, we see here as I explained continuity equation, here also no term has unit. So, dou u star, of course, you know already u star has no unit, t star is also no unit. So, the entire term has no unit. Similarly, other terms. So, the entire equation is without any particular unit, and one can extend this procedure to get non-dimensionalized y momentum and z momentum equation. So, if you solve for example this equation for one problem, then you see the advantage. If there is a change in any design parameter for that problem, then you need not repeat this calculation just for the sake of changed dimensions or changed design condition. We go to the next important topic, what is known as a vorticity stream function equation. There are certain difficulties while solving Navier-Stokes equation. What are the difficulties? One is a pressure gradient. Pressure gradient term appears on the right hand side, dou p by dou x, dou p by dou y and dou p by dou z. So, this pressure gradient term behaves like a source term, and if you have observed, we have a continuity equation and we have three momentum equation. Primary variables u, v, w are there in these four equations, but there is no separate equation for pressure, whereas the pressure is appearing in all the three equations. Dou e by dou x, this is the term, first term in the momentum equation, x momentum equation, convective acceleration first term, and function u multiplying its own derivative dou e by dou x is a nonlinear in nature. Hence, treating this nonlinear term is again a very trick. Now, you may have to do many iterations to get a solution. So, whether we can have an alternative to overcome these two main difficulty. So, if you can eliminate pressure term or and if you can get an equation where such a nonlinearity behavior is not appearing in that equation. Now, such alternative approach is what is known as a vorticity stream function formulation. Okay. So, we will do a detailed derivation of vorticity stream function formulation. The starting point is always again momentum equation. So, take a momentum equation and consider a 2D situation, which means you can consider x and y momentum equation, unsteady term. So, they are repeated here, x momentum equation and y momentum equation, and continuity equation is also written here for the sake of completeness. Now, what do we do? This is x momentum equation is referred to equation 1 and y momentum equation is referred here as equation 2. So, we are going to do some manipulation from these two equations and we are going to see that. Okay. So, differentiate equation 1, which is x momentum equation with respect to y. So, all the terms in the x momentum equations are differentiated with respect to y. We follow a similar exercise, equation 2, which is a y momentum equation, differentiate all of them with respect to x, then subtract the second equation from the first equation. So, mathematically it is given here. This is the first equation in this bracket, first equation, which is x momentum equation, differentiate with respect to y. Similarly, the second momentum equation differentiate with respect to x. Whatever you obtain, subtract one from the other. So, what we do, we will take term by term and see how this is done. Now, we will do that exercise term by term. Let us take the first term. First term is a time derivative term, and you see here dou v by dou t, which is coming from the y momentum equation, and that is taken derivative with respect to x. Dou e by dou t is coming from x momentum equation, that is taken derivative with respect to y. So, subtract and you are able to get this. Now, this partial derivative can be exchanged with this. Similarly, this partial derivative can be exchanged with this. So, common term dou by dou t is taken out and dou v by dou x and dou e by dou y term appearing inside the bracket. You can immediately recognize that dou v by dou x minus dou e by dou y we already defined, which is from the vorticity vector in the first class. So, this is one component of that vorticity vector, omega z component, and that is given by dou v by dou x minus dou u by dou y. So, if you substitute omega into this expression, then you get that equation, that expression is written here as dou by dou t of omega. So, this is the first term in the vorticity transport equation, the time derivative term, the first term in the vorticity transport equation. We will extend this procedure for the second term, which is a convective term. Again, you can recognize dou v by dou x, which is coming from the second term in the y momentum equation. Take a partial derivative with respect to x, then dou e by dou x, which is the second term in the x momentum equation. Take a partial derivative with respect to y, subtract one from the other, then take a common term dou by dou x outside, you get dou v by dou x minus dou u by dou y inside the bracket, and this term is same as what is shown here, dou v by dou x minus dou e by dou y, and we define that as a vorticity. So, you get u into dou omega by dou x. So, as you can see here, this is a second term in the vorticity transport equation. We are going to repeat this procedure for term by term to get a complete vorticity transport equation. So, finally, the resultant equation will look like this. First term dou omega by dou t we have seen in detail, u into dou omega by dou x we have seen, and v into dou omega by dou y you can derive. Similarly, you can repeat that exercise on the right hand side and you get an equation like this. So, if you look at this equation, the form, the way the equation looks all similar. We had a similar format for u momentum equation, except that the variable is now vorticity omega. Otherwise, you are again able to recognize this is a local and these two are convective kind of term, and if you put them together you get total derivative of expressed in terms of omega. The difference here is you see the function use u, but it is not multiplying its own derivative, it is a different function. Hence, the nonlinearity associated with the convective term in the original momentum equation is simplified in this equation. So, if I express in terms of total derivative t by dt of omega representing all the 3 terms here on the left hand side, and then right hand side is given mu into del squared omega. So, this equation 5 is actually what is known as a parabolic in nature. We are going to talk about equation nature next week. So, we will come to know what is parabolic in nature. Right now we just accept this is parabolic, and that equation 5 is what is known as a vorticity transport equation. So, in this class we have started momentum equation, went over the momentum equation once again, simplification of the momentum equation, obtain Euler's equation, Bernoulli's equation, then non-dimensionalization, some important non-dimensional numbers, and we did a detailed working on how to obtain non-dimensionalized continuity equation. It helps to avoid repeating calculation for different situation. Then we went on to do another important topic, what is known as a vorticity stream function formulation. In that we did the first part, how to obtain a transport equation for vorticity. We will close here for this class. So, next class we will start from here, obtain governing equation for stream function and relating vorticity and stream function and few more interesting topics. Thank you.